Good morning, everyone. A very good morning. Shall we begin the session? Today's topic is machine level representation of the program. That is, what are the various machine level representation, how we can represent the various material. That is a machine level representation of the program. So first is a historical perspective, that is in the page number 156, this one. Then program encoding, how to encode the program. Then data formats, what are the various data format that is available within the array or within the array bound, that is what are the various data that is used with this. Then accessing the information, how to access the information, what are the various drawbacks of accessing the information, what are the various ways by which we can access the information. Then arithmetic and logical operations, control, procedures, array allocation and the access, heterogeneous data structure, putting it together, understanding the pointers, how we can understand the pointer, what are the various ways by which it is used, then life in the real world using the GDB debugger, then out of bounds, memory reference, buffer overflow, then x86-64 expanded array, then machine level representation of the floating point program. At last there is a summary. Code, that is computer executes the machine code, that is a sequence of the bytes, encoding the same, that is a low level operation that manipulates the data, manage memory, read and write data or storage devices, and communicate over the network. So whenever we communicate over the network, so there are devices that is used to read and write the data, make the storage, make the communication over the network. And compiler also generates machine level code or the machine level instructions through a series of the stages based on the rules of the programming languages, instruction set of the target machine, convention followed by the operating system, and the GCC compiler generates its output in the form of the assembly language. So whatsoever it takes, whatsoever the compiler takes, that gives the output, generates the output in the form of the assembly code, that is a textual representation of the machine code. Binary code that gives the instruction, individual instruction in the program .ccc that invokes both assembler and the linker. That means this GCC code uses both the assembler and the linker. That assembler converts the assembly language into the machine language, and the linker converts assembly language or it links the executable code from the assembly code. And when the programming in the high level language such as C and even more so in Java, so we are shielded from the detailed machine level implementation for our program. And in contrast of it, or in usage of it, when writing the programming assembly code, a programmer must specify the low level instruction the program uses to carry out computation. And most of the time it is used with the reliable to work, high level of the abstraction that is provided by a high level language, and the type checking provided by the compiler helps to detect many program errors, make sure we reference or make sure there is a manipulation of the data in the consistent way, and with the optimizing the compiler, the generated code is used at least as sufficient as the skilled workers. That is used for the compile code, that is used for the execution with the number of the machines, with the number of the executable codes. Now, in this chapter, we will learn the details of our two particular assembly languages, that is how the C programs get compiled in these forms of machine codes. And reading the assembly code generated by the compiler involves a different set of the skills than writing the assembly code by hand. We must understand the transformation details, typical compiler, that is converting the construct of the C into the machine code that is used with the express C language, that is used with the compiler, the tree arranged execution order, eliminate unneeded computation, replaces the slow operations with the faster one, and used with the recursive computation into the iterative ones. And it is a form of reverse engineering. Try to understand the process by which a system was created by studying the system and working backwards. And in this case, the system is a machine-generated assembly program. So rather than something designed by the human, this simplifies the task of reverse engineering. That is, the generated code follows fairly regular pattern, and we can run the experiments having the compiler generate code for many different programs also. Now, our presentation is based on the two related machine languages. One is the Intel IA32 and one is the x86-64. That extension is to run on the 64-bit machines. That focus starts with the IA32. And there is also a technical presentation that starts with a quick tour to show the relation between C, assembly code, and the machine code that proceeds to the detail of the IA32. That starts with the representation, manipulation of the data, implementation of the control that is used with the construct such as if, while, switch statement. And with this background in the machine level programming, we can examine the problems of how to bound memory reference and vulnerability of the system to buffer overflow attacks. That is used with the part of the presentation that is used with the tips using the GDP debugger for examining the runtime behavior of a machine level program. And when we use the IA32 to the 64 bit that is used with the x86-64 that was originated, that is developed by the AMC, that is developed by the AMD, we can say, Advanced Micro Devices, that uses the 4 gigabytes, that is 2 power 32 bytes. And we also provide web asides to cover the material needed for the dedicated machine language that is used for the SSE. That also supports some multimedia applications. Now these are the various processors that is used with the complexity 8086, 80286, i386, 486, Pentium 4, Pentium 2, 3, 4, 4E, Core 2, i7. That is used with the Intel, that is used with the IA32. This is 8086, 80286, this one Pentium, this one. Now suppose we write a C program as two files p1.c, p2.c. We can compile this code on a IA32 machine level using a Unix command line, that is Unix gcc 010p p1.c, p2.c. That is used or that indicates a GCC C compiler with the default compiler on the line next, with a GCC compiler with a GCC command that is used with a C preprocessor. Then first one is a machine level code, machine level instruction that is also used as an instruction set with the ISA with the IA32 x86-64 that describes the behavior of a program with each instruction that is executed in the sequence, with one instruction completing before the next one begin. And the processor hardware is far below the elaborate, executing many instructions concurrently, but they also employ the safeguard to ensure that the overall behavior is to be implemented. Overall behavior is to provide a memory model that appears to be very large byte array that is used with the actual implementation of the memory system. Now, IA32 machine code differs greatly from the original C code that is used with the variable that normally are hidden from the C programmer. One is a program counter, then integer register files, then condition code register holds the information, then set of the floating point register that stores the floating point data. Now these are the various examples of the code that is used. So suppose we write a C code with the like the C code.c with the procedure file like int accum dot or accum equals to 0, then int sum int x comma int y, then int t equals to x plus y. That means we are taking the variable of the int type and stores the result or the addition of both x and y into the t, then accum plus equals to t, then return t. This is sum, pushL, moveL. This is used with the I32 instructions with the 0 to 15 or 1 to 15 byte. Let's start again. So we are studying the features of machine level language or the machine level code as well as the deassembled representation, that is IA32 instruction that can range from 1 to 15 bytes. Instruction format that is used in such a way that starts with the position with the unique decoding of the position with the bytes that is used with the machine instruction. For example, when we use the instruction push L ampersand EBP that starts with the byte value 55, and the or the disassemblers determines the assembly code based purely on the byte sequence in the machine code file that is used with the access to the source or the machine code versions of the program. And the assembler or the disassembler uses a slightly different naming convention for the instruction that does the assembly code generated by the GCC. In our example, this is used with a suffix 1 from many of the instructions. Now, when we generate the actual executable code that requires running a linker on the set of the object code files, one of which may contain a function. Suppose in a file main.c we had the following functions. This is int main return sum 1 3. That means the sum is returned with the 1 3, 1 comma 3 in the sense the output is presented or represented as a 4 because the 1 plus 3 is 4. That is returned by the C program. Then we could generate an executable program as follows. This is GCC 010 program code main.c. This is the main C program that is used with the two procedure, but also use the information used to start and terminate the program, as well as to interact with the operating system, that is used with the bytes, that is used with the file program, that is used with the coding. Now the disassembler will also extract the various code sequences that includes the following: disassembly of the various file function sum. And the assembly code generated by the GCC is very difficult for a human to read. On the other hand, it contains the information with which we need to be concerned, while on the other hand, it provides a description of the program, that is how it works. For example, suppose we write the program simple.c contains the following code. This is int simple int pointer xp, then int y. So we are taking two variable. One is for the pointer, that is pointer xp. One is for the only y. Then t equals to, we are taking next variable, that is t again of the integer type, pointer xp. Pointer xp means xp contains the address of next function plus y. Then xp equals to t, return t. So when GCC is run with the flags S01, it generates the following simple files. This is file simple.c, global simple, this is simple.function, this is pushL, moveL, moveL, moveL. These are the various addition function, moveL function, addition function, populate function. One is push, one is pop. Push means inserting, pop means removing. Then ret, retry, then size, simple, then indent or the indentation. This is GCC Ubuntu 4.3.2, Ubuntu 4.3.2. Then dot section, dot node, GNU stack, dot program bits. And all of the lines beginning with the dot are the directives to guide the assembler and the linker, and we can generally ignore these one. On the other hand, there are no explanatory remarks, that is about how the instructions or how they are related with the source code. That gives a clear representation of the assembly code with the directives. So first of all, there is a push shell. This saves a frame pointer. This is create the new frame pointer, retrieve the xp, retrieve y, add the xp to get the t. Now xp pointer is added with the t. Then store the t at the xp. That means store the t variable at the xp pointer. Then restore the frame pointer, and then at last there is a return value. So we typically show only the lines of code relevant to the point being discussed, and each line is numbered on the left for the reference and annotated on the right by the brief description of the effect of the instruction and how it relates to the computation of the original C code. That is stylish with the versions of the way how the assembly language programmers format their code, format their tool. Now this is ATT versus assembly code format. This is simple: push EBP, move EBP, ESP, EDX, DWORD, PTR, EAX, DWORD, PTR, then DWORD, PTR, EDX, EAX. Then populate the EBP, then at last there is a return value. Now we see that the Intel and the ATT format differ in the following ways: that contains omit the size destination suffix, then omits the percentage character in front of the register names using the escape instead of the escape. Then Intel code have a different way of describing location in memory, for example DWORD, PTR rather than the 8 ampersand EBP. Then whatever the instruction that is used with the multiple operand list, that will reverse in the reverse, or that will do in the reverse order. That will be very confusing when switching between the two formats. Now next is the data format. that uses a 16-bit architecture, then expanded into the 32-bit one. Then Intel uses a word or term word to refer to the 16-bit data type. Based on this way, they refer to the 32-bit quantities as the double words. And it also refers to as the 64-bit quantities as a quad words with the 4 bytes double words. This is a C declaration. Intel data type, assembly code suffix. This is the size in the byte. This is char, byte, B1. Short word W2. Int double word 14. Long int double word 14. Long int. Char pointer float double long double. Next is accessing the information. How to access the information with the i32 or IA32 CPU that contains various 8 registers storing 32-bit value. These registers are used to store the integer data types, integer data as well as the pointers with the diagrams with the 8 registers. Their names all with the %E, but otherwise they have a peculiar names. With the original 8086, the registers were 16 bits and each had a specific purpose. Then operand specifiers or specifier that is used with the immediate for the constant value that is used with the AT&T format assembly code with the ampersand sign. Then memory reference addressing modes with syntax IMM.